All right, friends, you survived the enormous theory section where we built up our arsenal of deep learning techniques. And so now we're going to have a bit of fun in the TensorFlow playground so that we can get an intuitive sense of how we can apply these techniques in real life with real data. So this is such a fun little tool. It's available for your use as well at playground.tensorflow.org. And it allows us to use a lot of the theory that we just covered, and we can see everything as we change parameters, really get a sense of how these things work. So let's describe the problem here. We've got a really simple input. We have two inputs, x1 and x2. One of them is a vertical axis. X2 is a horizontal axis. And we have a relatively simple classification task for this neural network to solve. So this is a super simple neural network here. It only has one neuron in one hidden layer. So these x1 and x2 represent this first layer right here that we drew on the board. Our hidden layer is just this one hidden layer for now. That's all we have is this one, which is one neuron. And then we have one output neuron as well, because we're just guessing one class. We're guessing whether we have orange dots or blue dots in this two-dimensional image. To go over some of the other terms that we used here, we're using a tanh neuron. You can see that right up here. That's our activation choice. And let's see how we can perform. Let's see how well we can distinguish these orange dots from these blue dots by pressing play. So let's talk about the things that are happening here. So epochs are the number of times that we're running through all of our data. So all of these points that we have. And we talked about epochs before. In lesson 1, we ran our network for one epoch and the learning wasn't very good, but then we ran it for more than 100 epochs and we started to get pretty good classification accuracy on those MNIST digits. We had something like 86% accuracy. So let's pause here. So we've now trained for 546 epochs on this very simple problem with this very simple artificial neural network. And we can see here, this chart is showing our reduction in loss. So loss is a synonym for cost in cost function. And so we have our test loss is this black line, which is the performance of the neural network on data outside of the data it was training on, so unseen data. And then the training loss is its performance on the training data itself. So that's the gray line beneath. So you can see that over time, over these 546 epochs, we improved on both our training loss and our test loss, and then we plateaued. So learning kind of stopped. And I think with this very simple architecture that we have here with a single neuron, this is about the best we could hope for. A little bit more terminology here. We talked a lot about weights between neurons, and we can see those as the orange lines here connecting. We can even, if you hover over it, it tells us the weight, and you can actually input your own values to see what impact that has, so you can play around with that at home. And we see that this first neuron, x1, has a greater input, so it has a weight of negative 1.3, so that's more of an impact than x2 in terms of magnitude, and so that shows up as the thickness of this line, of this tensor. First time we're using that word. This is a tensor between the two neurons. And then we have another tensor here from the only neuron in the hidden layer to the output layer. So let's make this a little bit more complicated. Let's make it look exactly like this this network here on the board. Well, except that we're still going to leave it with two inputs, but let's have two hidden layers. So now we have two hidden layers, and our first hidden layer here has two neurons, so let's add one more neuron. And then our second hidden layer here has three neurons, so let's add a third neuron to that second layer. And then our output, still just a single output. We only have one class, 1 or 0, that we're trying to guess here. So let's see how this network performs when we train it. So now look at that. That is getting to much lower values on both our training and our test loss. We're plateauing a bit now. So let's stop there. So 300 epochs of training. Now, this is interesting. The shape that the network was able to fit is now quite a bit more complex. It's nonlinear. So when we only had that one neuron, we could only try to fit a linear boundary between the orange dots and the blue dots. But now that we have these 5 neurons in the hidden layer, it can start to make these complex shapes. And in fact, one of the beautiful things about this TensorFlow Playground tool is that you can see what's causing this neuron to activate. So in the first layer, we have one that's good at distinguishing along this diagonal, and then this other neuron is good at distinguishing right along on the vertical. And we see that this top neuron in the first hidden layer is passing a strong positive weight into this neuron down here. Likewise, this neuron is passing a strong weight into this neuron down here. And we can see that together, this kind of vertical shape is having an effect here in this neuron with this vertical line here. And this diagonal shape is visible here in this diagonal line. So you can see how these higher layer neurons can create more complex abstractions, nonlinear abstractions of the neurons in the layer below. One thing that we've mentioned a number of times, but I haven't yet in this little section, is that, of course, these are all dense layers. So we talked about a couple of different kinds of layers now. These are just dense layers here in the middle, where all of the input neurons are connected to all of the neurons in the first hidden layer, and likewise all the way through the network. Everything's connected. However, so when we started this network, the weights between all of the neurons were randomly initialized to random small values. And then as we let the network learn, the weighting on some of these connections becomes much stronger, while the weighting on other connections is dropped. So you can see some of these weights become quite strong, whereas other weights become weaker. Now, we can do even better. So what are some ways that we talked about in the last section that will make learning faster and better in this demo? Well, we talked about ReLU neurons potentially being more efficient than TANH neurons. So let's change that activation here. We're going to change to ReLU. We are going to add more hidden layers and more neurons to each of those layers. And now let's see how this network performs. Now look at that. By providing this network with even more flexibility, we have even more complex abstractions, particularly a circle here. And that ends up being that this top level neuron on its own appears to, with the inputs from the earlier hidden layers, do most of the work of classifying these blues from these oranges perfectly. And you can see our training loss and test loss both go down to essentially nothing. Now, that gives us some insight. It means maybe we only need one neuron in our top layer. So let's see what happens if we do that. It seemed like only one neuron was doing all the work, so let's test that hypothesis. Yeah, here we go. That neuron all on its own is able to do the work. And one other thing that's worth mentioning here, we've talked about these tensors representing weights with large positive weights corresponding to thick blue lines, large negative weights corresponding to thick orange lines. In addition, you can see the biases, B, on each of these neurons, which is this dot. So this bias 1.2, this lighter shaded bias is only 0.52, and then this negative bias here is negative 1.2. So visualized here, we have all of the elements of our diagram here. We have the weights, W, are represented by the tensors in between neurons. The X's are represented by the inputs here, so the vertical and horizontal axis values. And then The bias B is these dots next to each neuron, and the activation is the result of Z, the sum of our weights and the dot product of our x's plus our biases is our Z. Pass that Z through some activation function, which is now ReLU, or previously we were using Tanch in this demo, and those are passed along to the next neuron in this network. So everything's starting to come together here. Now, what happens if we make this a more complex task? So distinguishing these orange and blue dots in these circles here, that's a relatively simple classification task. So what if we switch over to this classification task where we have these swirls of blue and orange? That's going to be trickier. Let's see if the network that we just had that fared very well with the circle, let's see how it fares here. It seems to be getting stuck. So, oh, no, then we made a bit of a breakthrough. So our training loss is going down, but our test loss is going up. So that means that we're overfitting because the training examples are saying, hey, I'm getting better and better and better answers. But when we try to generalize on test data outside of the training set, the performance isn't really improving. So it seems like our network is not properly built for this kind of classification task. So what kinds of things can we do? Well, we can add another hidden layer. That allows us to have more levels of abstraction. And then maybe let's add some more neurons in the bottom layers, because then we have more kinds of simple edges and things that we can pass to have turned into more complex representations higher up. So let's try that architecture. Takes a little bit longer to learn. Oh, but yeah, it's learning well. Look at that. Our training loss is going down. Test loss is holding steady. Can we make a breakthrough? Doesn't look like it. Looks like this network is a failure as well. So let's try adding even more hidden layers. Now this is going to take longer to compute because we have more and more weights and biases to calculate on each pass through backpropagation to learn these weights. But let's see if this network can learn well. Training loss is going down. Test loss is going down. How are we doing up here? Man, seems like we're stuck again. I thought for sure that would work. So that architecture with 6 hidden layers wasn't working for us. So I've taken this completely different course to solving this problem. I've reduced the number of layers from 6 hidden layers to 4, and I've increased the number of neurons in the first layers. So let's see how this performs now. Our training loss is still going down. Training loss is still going down. Bam, we made a breakthrough. So we're starting to get the right representations. Oh yeah, this is looking really good. Our training loss is going down towards 0. Our test loss is almost 0 as well. Let's pause the network there and have a look what's going on. So once again, as we were seeing with the simpler networks, the first layer is capturing simple edges, so orientations. And then the second layer is capturing mixes of those orientations, so creating these kinds of wedges, creating some simple kind of triangle shapes. And then the next level of abstraction is able to take any of the abstractions in this second hidden layer and create circles, this kind of curvy shape here. This curvy shape ends up being a really great fit with the network here. And then finally in the fourth layer, we end up having this neuron right here, which captures the shape very well here to distinguish blues and oranges. So you can see that this neuron here actually isn't doing anything. It's basically dead. It has almost no inputs going into it. And this neuron right here is doing the bulk of the work in the final layer. So pretty cool. We cracked this. So you can have some fun in here yourself. You can try some regression problems, which aren't just straight classification, but then you're trying to guess values between 0 and 1. and you can play around with plenty of different architectures there. So there you have it. We've used this TensorFlow playground to build a pretty complex neural network that's solving a pretty complex problem. Next, we're going to talk about some bigger data sets that we'll be solving problems on later on. And then we're going to get back into writing code in our Jupyter notebooks to be building deep networks like these ourselves. I'll see you there.